Hello class, this is CSE-5250, Section 60, and Section 1, Week 9, Fall 2023. Now, due to an agreement I made with the in-person section, that's Section 1, this video and all successive videos will now be made available to all sections, basically. Now, for this week, we are looking at MPI, but before I get to that, I would like to briefly say a few things. Hopefully you're getting progress done on your midterm project. You are to write a program and then benchmark it. I will say right now that if you are if you're gonna try the program, although it's not mentioned here, you can go as far as you want. So I say go up to 1 million, but you can go up to 1 billion. On the other hand, you could go up to 100 and see whether that works. In any case, you would want to try the program with different numbers of threads. So 1 thread, 2 threads, 4 threads, 8 threads. If your computer is capable of doing so, you can try 16 threads, or possibly even 32 threads, depending on what kind of CPU you have. Anyway, that's one thing worth mentioning. The benchmarks table that I have in this file, it's really a starting point. You can go as far as you want. However you get your execution times, just be sure to get an average by running the same combination of thread count and search max at least 5 times so you can get an average execution time. The more the better. Okay, so Section 1, we talked about this in class. We went through the answers for the first 2 short answer questions, and I've since graded them. They're graded for both sections. These questions are graded on whether you attempted to answer them. So it doesn't matter if your answer is wrong or right or halfway there or anything like that. What matters is you attempted to answer the question, because I'm going to discuss the answers right now. The first question was, what is MISD? Well, recall to Flynn's taxonomy, it is a classification of 4, maybe 5, and depending on where you look this up, maybe even more than that, ways of classifying parallel hardware. We can generally divide it into number of data streams and number of instruction streams. So SISD is standard sequential programs. 1 instruction stream, 1 data stream. This is what we call boring for the purposes of the class, because it's just one process doing one thing, one at a time, one after the other. So we don't want that. We're more interested with this column here of having more than 1 data stream. So SIMD, MIMD, and a thing in the middle called SPMD. We're not really looking at MISD because this is 1 data stream, multiple instruction streams. You can think of it as I guess one way to answer is to consult, for example, you could look up the Wikipedia definition on this, depending on how well it's written, of course. This article is written like a personal reflection, personal essay, or argumentative essay that states a Wikipedia editor's personal feelings or presents an original argument about a topic. Please help improve it by rewriting it in an encyclopedic style. April 2017. So that's one concern about Wikipedia. Not everything might be up to date. And if it is up to date, if you're lucky, you will get footnotes that will take you to sources that the Wikipedia article uses. The point is, if we tease through what this says here, we don't really use MISD for parallel programming applications. But what it does is, MISD is a type of parallel computing architecture where many functional units perform different operations on the same data. One way to think about it is you have a data set and you want to find the mean, the standard deviation, the variance, all of that, all at once. Another way is you have a maze, but you want to traverse the maze and find the exit. You say run multiple instances of the same program, or have one program split into multiple threads, and then have each thread traverse a different part of the maze. If one thread reaches the end, we say that we successfully exit the maze, and maybe we can find the path that thread took. If not, and say one thread hits a dead end, it must be able to backtrack and go back the other way and try again on some other branch. So we're not really looking at MISD in this class, because, as mentioned, they don't really lend themselves well to the kinds of parallel programming that we typically think about, where we have so much data that one process cannot possibly go through it all in a reasonable amount of time. So we create multiple instances of the same process, but they're all working with one another, so that each process gets a portion of the work, and they do the same work in parallel in the hopes that we reduce the execution time. My brother has a project where if he did not use parallel programming techniques, it would take him 7 years to create his data set. But with the use of MPI, he was able to get that execution time down to 3 weeks. So that's why we need parallel programming. There are just tasks that are just way too big to do. Some tasks that are way too big to do on a single process. So that's the answer for what is MISD. I also asked you a question on what would happen if we tried to parallelize the for loops in here. So I only asked you to think about what would happen if you parallelize the first for loop, and then think about what would happen if you parallelize the second for loop. What happens here is we have a program that's calculating consecutive Fibonacci numbers by using the previous two Fibonacci numbers to calculate the next one. What we have is a loop carry dependence. Therefore, this is the kind of for loop that we do not want to parallelize. So if we try to parallelize it anyway, well, what happens is there are many forms that a for loop can take on that OpenMP will flat out reject. So OpenMP cannot parallelize those kinds of for loops. However, this is an example of a for loop that OpenMP can parallelize, but the output produced is, well, garbage, because we did not take into account that loop carry dependence. So what happens is this. We have an array of 40 Fibonacci numbers. We calculate the first two. So in the case of one thread, that single thread is going to calculate the next 38 Fibonacci numbers by taking the first two numbers and then adding them together to get the next number. And then the next number is the sum of the first two numbers before that. And the next number is the previous two numbers before that. So with one thread, it will go one by one in each element in the array and then calculate the next Fibonacci number. If we had two threads, one is calculating the first 19 Fibonacci numbers after the first two. The second one is calculating the next 19 after that. The problem is when we initialize this array, it's going to have something in memory. Of course, we have something in memory already. It's the 1 and 1 as the first two Fibonacci numbers. Is that we never assigned anything for the other 38 numbers after that. Not even a 0. So it's going to have something in memory, but we never inspected what it was. So it could be whatever was there in memory already. So when the first thread goes and calculates the first 19 numbers, they're going to be correct. When the second thread starts, it's going to start at the same time as the first thread, which is calculating its 19 numbers. The second thread is calculating its 19 numbers. Without any synchronization, the second thread is just going to add whatever there was in memory, and then we get random garbage. So that's what happens if we try to parallelize the first for loop. If we try to parallelize the second for loop, again, these are two for loops that we're parallelizing separately. Parallelize the first for loop, you'll get random garbage. Parallelize the second for loop, if we did not parallelize the first for loop, it will work as expected. It's just that here there isn't a loop carry dependence, but that's just because there isn't doesn't mean it's a good idea to parallelize it. Simply put, it will print the numbers in a random-ish order. So that's the answer to the second short answer question. Once again, for section 60, I'll be grading these in the coming week based on whether you attempted to answer it. Alright, with that out of the way, let's finally look at MPI. And what better way to start than with a little bit of review. So, in the world of parallel multiple instruction, multiple data computers, we have what are called shared memory and distributed memory systems. So this is a review from chapter 2. So we can either have one big block of shared memory that all the CPUs are sharing over an interconnect. Or, this is a shared memory system. Or we can have each CPU have its own private memory, and then those CPUs are talking to one another over an interconnect. For our purposes, we want to write something that can take advantage of that. So we're gonna start parallelizing our programs using MPI. It is an abbreviation of Message Passing Interface. MPI is not a new programming language. It defines a library of functions that can be called from C and Fortran programs. As you can tell by the name, what makes this work is the idea of message passing. So, a few things worth knowing. When you think of a program, any program, maybe your favorite video game or a special program that you use to do something, we think of in the context of operating systems, we have special names for whether a program is sitting on your hard drive or being executed by the CPU. If it's sitting on your hard drive, then a program is nothing more than a file whose contents is basically instructions that the CPU can understand. Or maybe the CPU can't understand it and some interpreter program has to read it, and then the CPU can understand what's being interpreted. So that's just a program. A process is when you have a program that's loaded into memory, and then the instructions are being fed to the CPU to be executed, and then the results of that execution are then stored back into memory. So that's a process. A process is simply a program in execution. What we're doing is we're writing multiple processes. Actually, no, we're writing one process, but we are going to create multiple instances of the same process. We can get started by simply writing this Hello World program. This program is available on Canvas due to a request. By request, I made this program available on Canvas, so instead of just typing everything out, you can copy-paste the code into a file. If you are on a Unix system, what you can then do is type in this command, npicc-g-wall-o, npi hello, or whatever executable name you want, and then npi hello.c. That npi hello is the name of the program and the name of the source code file. You would replace that with whatever names you have or want. So this is the Unix command to compile the program. If you can successfully run this without any issue, then you're basically free to proceed to the next step, which is to execute the program. There's a separate command. It's not just /executable name. We need a special command to run our MPI programs. That command is npi exec -n number of processes /executable name. If you are on a Windows system and you are using Visual Studio, I have special instructions for that later on in the video. For now, let's tease through how the program itself works. When we run this program, and this is in PowerShell, it doesn't matter if it's PowerShell or a Unix shell, you should have the same output. Here, I'm running the program using four processes, and I am getting simply a greeting from each of the four processes. When we write our MPI programs, we do so with the expectation that we don't know how many processes we're going to run it with. Or, put another way, we don't know what kind of computer we're going to be running our programs on. Generally speaking, we write our programs in such a way that it can be scaled to any number of processes that we want. So, it doesn't matter if we run it with 4 processes or 4 million processes. If it works with n process, where n is a small number of processes, it can work with a really big number of processes. So this is a modified Hello World program that we can use to demonstrate all the simple features, all the basic features of MPI. This is just a intro to MPI. Speaking of which, even if you couldn't attend the seminar on MPI that I announced about last week, they have their own PowerPoint slides that you can use, that you can refer to if you need any extra guidance on MPI. There are also online resources, because one of the big things right now in technology is something called high performance compute. This is a manifestation of parallel programming, where we have so much data that we need to process in a short amount of time. This is why parallel programming is important, because we have long since passed the point where we can just wait for computers to get faster, because they can't get any faster. At least they can't get any faster in terms of clock speed. If they did, we should be at a 1 terahertz CPU by now? We've only just reached 5 gigahertz. By the way. Yeah. And that's just the top of the line CPUs. The top of the line non-server CPUs can currently get up to 5 gigahertz right now. Or something close to it. So if you want a faster computer, we cannot rely on Moore's law alone, if we think about Moore's law as a periodic doubling in clock speed. Anyway, this is why we have MPI and all the other APIs related to parallel programming. So let's look at what MPI does. if you're to go through the source code of that Hello World program, you'll find that a few functions come in pairs. The first pair of functions is the MPI init and MPI finalize functions. The first function does all the setup necessary to set up, well, it does all the setup necessary so that you can use all the other MPI related functions. This is a function that requires two arguments to be passed in, just pass in null for both of them. So that's what MPI init does. It initializes the program so we can use all our MPI functions. When we're done with using MPI, we call MPI finalize. This frees up any resources used with MPI, and you must call this after you have called the last MPI function. This also takes in an argument. It takes in one argument. You can just pass in null for that. In short, call MPI init before you do anything with MPI. Call MPI finalize when you are done with using MPI functions in your program. Also note that a lot of these MPI functions, they have a return value that's an integer. If you are having issues, you can store that return value in an integer value and then determine what that error code is, and then you can debug your MPI program that way. So these functions and all other functions, they return error codes just in case you need to do any debugging. Now we get into the concept of what is called a communicator. In OpenMP, we have the concept of a team. A team of threads is where one thread, the master thread or main thread, creates. In MPI, we have that master thread or main thread where it creates a bunch of threads until it reaches a specific number of threads. That group of threads is called a team. The MPI equivalent of that is called a communicator. This is a collection of processes that can send messages to one another. One thing that we can do in MPI is specify different communicators. We deal with only one communicator in our example program that is called MPI COM world. So this is a collection of all of the processes that we create when we have called MPI exec. So if we call this with 4 processes, the communicator MPI COM world has 4 processes. We also have another pair of MPI related functions. The first one is called MPI COM size. The second one is called MPI COM rank. When a process is running on a computer, it thinks it has the whole computer to itself, even though it doesn't. What happens in the context of operating systems, one process will be executed on the CPU for some amount of milliseconds, or maybe possibly microseconds, and then it's taken off the CPU so another process can run. The only indication that these MPI processes, the only thing that these processes know that there are other processes in existence is the fact that each process can call each. Let me go back. When a single process runs, it thinks it has the whole computer to itself, unless we have it set up so that process can communicate with another process. In MPI, the only indicator that a process has to the existence of other processes is MPI COM size and MPI COM rank, or rather, calling those functions. MPI COM size gets us the size of our current communicator. So if we pass in MPI-COM world, that is our set of processes that can all talk to one another. And you pass that in with the address to a variable called, say, com size, that will get us the number of processes in our communicator. If we call MPI-COM rank and we pass in the communicator, say, MPI-COM world, and the address to a variable called, say, my rank, that will give us the rank number for that process. So if we go back to this program here, the com size for MPI-COM world in this program is 4 processes. Each process has a unique ID called a rank. Those ranks are 0, 1, 2, and 3. Keep in mind that numbering in programming typically starts at 0, with a few weird exceptions found every now and then where it starts at 1. The only examples where I can think of where numbering starts at 1 is Lua and MATLAB. But for our purposes, we think of numbering starting at 0. Back in OpenMP, there was a pair of functions. One gave you the number of threads in the current team for the program. The other one got you the thread number. If a thread were to call OpenMP's function for getting the thread number, that thread will get its thread ID, basically. MPI com size and MPI com rank are fulfilling the same roles as those two functions from OpenMP. It's just that now we are dealing with processes rather than threads. So let's tease through this for loop here. When we ran that program, it ran multiple instances of the same program as multiple processes. Each process is running the same code, really. So really we have multiple programs, multiple copies of the same program. It's just that they're all communicating with one another because they are part of the same communicator. Each of those processes has its own ID. But if we look at this snippet of code here, basically, certain processes are being told to do specific things based on the rank. So simply put, we have an if statement that says, if you are not rank 0, do this code. Otherwise, do this other code. This kind of programming is common with most MPI programs. But more broadly, this use of an if-else statement, that is typical of SPMD programming. Basically, we are creating multiple copies of the same program, or I should say running multiple copies of the same program, and we're telling each copy what to do based on its rank. If you are not rank 0, do this code. If you are rank 0, do this other code instead. So what's that code do? We'll get into that in a little bit. In principle, the program will run with any number of processes, and as I said, we don't know how many processes we will need, so we write them in such a way that it can be run with any number of processes, whether it be a few dozen or a few million. So let's look at what this code does. If you are not rank 0, send a message to the process whose rank is 0. How I talk about this is a little bit confusing, so if I say send a message to rank 0, I really mean send a message to the process whose rank is 0. If you are rank 0, you are going to receive a message from all other processes. So, we have 4 processes being executed, and one of them is going to receive a message from all other processes. Now we look at another pair of functions called MPI send and MPI receive. So let's consider the simple case of one process sending a message to another process. If you are not rank 0, send one message to rank 0. So let's look at the send first. There are 6 parts to it. Or I should say there are 6 arguments to it. There needs to be a corresponding receive function in here, for example. So what this for loop says, we are iterating through a for loop and calling the receive function for each process there is that is not rank 0. We do this so that we pair every send with a matching receive. If we don't do that, the program breaks. Or I should say, the program won't work. There are some specific details as to how it doesn't work in the textbook. If you have the textbook, you can look into that as well. But I'd like to get into what are we sending anyway. MPI send has 6 arguments, and this is also a function that has a return type of int. So if something goes wrong, we can do debugging based on the error code that was returned. So what are those 6 arguments anyway? The first argument is a pointer to the block of memory that contains the contents of the message. So if we go back to the source code, we have a constant integer max string. That is a maximum length for our buffer that we called greeting. So this greeting is our buffer. The first argument is a pointer to the block of memory that contains the contents of our message. That was our buffer back there. The second is the size of the message. How many bytes big is our message? The third is the data type. Let's go back to that buffer itself. So let's look here. The send function has the address to the greeting itself, character greeting, and then square brackets max string. So just pass in the greeting for here. We pass in as a second argument, how big is that thing? We can just simply pass in strlen greeting +1. And this is an array of characters, so the data type is MPI character, MPI char, or is it car? Anyway. Here's a list of all the possible data types that MPI supports. We can have characters, integers of varying lengths. We can have unsized integers. We can have floating point values. We can pass all sorts of data types through MPI. The fourth argument is the rank of the receiver. The fifth argument is a non-negative integer that we call a tag. This is used to differentiate between 2 messages of the same size and type. So we can use a tag to, for example, say, don't print this message, do not print this message, use this for computation. And we can assign that to be tag 0. And then tag 1, we can say, okay, don't do any computation with this. Just print it out for debugging purposes. So that's what a tag is for. We use a tag to identify what kind of messages we have if we have messages of the same data type and we don't want to mix them up. For our Hello World program, don't worry about the tag, just set it to 0. We're not really using the tag for the Hello World program, so we can simply set that to 0. The last argument is the communicator. In our Hello World program, we have one communicator called MPI ComWorld. in MPI, we can create different communicators, and then we can use that as our sixth argument. The point is, a communicator is a set of processes that can all talk to one another. If we have MPI COM world, we can have, for example, if you have MPI COM world and there are 4 processes, we can, for example, set up a separate communicator for 2 of the processes. It's as though as MPI COM world was a communal Discord server, but some of the processes have their own separate Discord servers for coordinating and communicating about different things. So that's what a communicator is. Or rather, that's why we think about communicators, because, yeah, we have the main global communicator in MPI COM world, but sometimes we might need a separate communicator for separate processes. For our purposes, you can just simply pass in MPI COM world. MPI receive has 7 arguments, but the first 6 correspond to the 6 arguments needed for MPI send. The first one is an argument to the pointer to a buffer that store the incoming message. So basically, you could think of it as a mailbox. The second one is how big is the message? How big is the message itself? The third is the data type. We looked at data types previously. They all start with MPI. Everything in MPI starts with MPI. The fourth is the rank of the process who sent that message. The fifth is a tag. The sixth is the communicator. The seventh argument is something called MPI status ignore. Yeah. Because for now, we are not really looking at the status for now. So we can just simply ignore it for now. But we have a use for a status that I'll get into in a little, that we'll get to later on. When we send one message from one process to another, the tags must match. The communicators must match. If a process were to send, if a process Q were to send to process R must receive from process Q. So process Q calls send, and it's sending to process R. Process R must receive from process Q. If we mismatch any of these, the program breaks. One thing to consider is this. It's possible that one process may end up finishing before another process. Say we have 100 processes whose IDs are 0 to 99. Process 0 sends a message to all the other processes, starting from 1 and then ending at 99, instructing each process to do some sort of work. Then, process 0 receives messages from processes 1 to 99. So, after processes 1 to 99 do their work, they send that work back to process 0. And due to the nature of parallel programming, it's possible that one process might finish sooner than another. Process 0 has no way to know which process had finished. If process 2 had finished before process 1, what happens is this. Because of the for loop, we are using this I here as our... Okay, in this receive here, it means we are receiving a message from process 1, and then a message from process 2, and then a message from process 3. If process 2 had finished before process 1, process 1 would have to basically wait. If process 2 had finished before process 1, process 2 would have to wait for process 1's message to be received before process 2's message could be received. So by writing our receive function as part of a for loop, we enforce a way of synchronizing the order in which we receive processes. But if we're in a situation where we don't care about the order, then if it's more important that we receive whoever's work was finished first, then instead we call MPI, we use MPI any source as the argument, the fourth argument for our receive function. We have a similar situation that can happen with the tag, so we have another wildcard tag as it's called. No, we have another wildcard as it's called for the tag. Simply put, if we look at this receive function, we can specify who was sending the message, who was the sender. We can also specify what was the tag. But in MPI, we can replace this fourth and fifth argument with wildcards. So it basically says, I don't care who's sending it to me. I want whatever came first. I'll show you what that looks like in code in a little bit as well. So here's the rules about wildcards. Because of the wildcards, MPI is what's known as a push communication mechanism, not a pull mechanism. The other thing is, we can only use wildcards for the receiver, not the sender. There's also no wildcards for communicators. So that's the end of that slideshow. Now I'd like to take the time to show the program itself in action. Now, if you are on a Windows system and you want to run this program for yourself, there are special instructions that you need to follow so that you can get the program to work. If I can pull them up real quick, then here we are. On Canvas as well, there are special instructions on how to install MPI on Visual Studio. You only need to do this once. This is Microsoft's implementation of the MPI standard. That's why it's called MS-MPI. But for our purposes, it's the same MPI that we would be using on any other platform. If you want to do this on the lab computers, it should also work. But if you want to do this on your home computer but you have a Windows system, then you need to do these instructions first. Step 1. Go to this link and download Microsoft MPI. Click here, and when you see the screen that says choose the download you want both MSMPI setup.exe and MSMPI SDK.msi. You need both of them to not only run programs, but to write these programs. After downloading, run MSMPI setup. When it says, do you want to allow this app to make changes on your device? Say yes. You let the installer run, and then you run the second installer, MSMPI SDK, and then you follow those steps. Once you're done, once you've completed these 5 steps, and let me emphasize again, there are 2 installers and you need to run both of them. Once you're done, MPI will now be installed on your computer. So, this next set of instructions is how to create a Visual Studio project that uses MPI. Open Visual Studio and make a new C++ project. Yeah, these are all C programs, but it is possible to retrofit these programs so that they work with C++. It's just that we can't really use the C++ data types for our messages. The point is, if we want to run this on Visual Studio, we need to follow these instructions. There are 3 things that we need to do to make our program compile, basically. So what you want to do is create a new project. Make sure you choose the console app. Name your project, choose a location for your project. When you open your project, what you need to do, well, of course, you need to add in include npi.h in angle brackets. Angle brackets. When you do this for the first time, what will happen most likely is you'll have red squiggly lines, a red squiggly line under include npi.h, and possibly every other NPI related keyword. Here are the steps that we need to do to make our project recognize NPI. It's a 3-step process, and one of the steps depends on what kind of project you are making, so you'll need to pay careful attention here. Click the Project tab. Click the Project tab, go to Project Properties, under C/C++, click Additional Included Directories. Edit. A little window like this will pop up. If you click this dot, if you double click this, a little button with a ... will appear. Click that, and what you should do is navigate to where your NPI SDK files are. So the path should look something like this. C:, and if I can do this, it should look something like this. C:, program files x86 / Microsoft SDKs / NPI / lib. And then, depending on whether your program is x86 or x64, depending on whether it's 32-bit or 64-bit, you want to choose either the 32-bit folder, that's x86, or the 64-bit folder, that's x64. You want to select the appropriate folder because if you look up here, my project is x86, so I had chosen the x86 folder. So that is that's the folder you have to search for. Alternatively, when you install the NPI SDK, if you did not change the install location at all, you can just simply type in this entire string here. So that's the first step. We need to include the library. No, not to include the library. That's actually the next step. We had to include the include directory. So that was the first step. Once that's done, we click OK, but we're not done yet. That was the include directory. We need the library directory. What we do next is we go to linker and go to additional library directories here. Click edit. A similar window will pop up again. If you click on it, or maybe double click it, another similar ... button will appear. Click that, and you'll get a similar pop-up window from before where you can simply type in C:, program files x86 Microsoft SDKs NPI lib x86. You would select the appropriate folder depending on whether it's x86 or x64. Click OK. And then the final step is to go to expand this and look at input here. Type in msmpi.lib as an additional dependency. So you click edit, you get a little window like this. You type in msmpi.lib. So, as a recap, additional include directories, you add in this path here. Actually, that should be msmpi. That's actually the wrong one. That's the correct path. So it's actually C:/program files x86 Microsoft SDKs MPI include. So that is our include directory. You type that in for your additional include directories. Then you want linker general additional library directories. Edit. You'll get a window like this. Type in or look for C:/program files x86 Microsoft SDKs MPI lib, and then either x64 or x86 depending on what kind of program you're making. You select that folder, click OK. Click on input additional dependencies, and you simply type in msmpi.lib. Apply. Click OK. It broke. But those are the instructions you would have to do. Maybe what I'll have to do is create a separate video that clarifies all these instructions. So, yeah, in case you're confused about this, I can create a supplementary video that does this once and for all. So maybe I'll just pause the recording here and okay, so once again, and the hardest part really is just getting it to work. Under C/C++ general, additional include directories, it's the path to the MPI include folder. Under linker, under additional library directories, it's going to be the path to either the x64 library or the x86 library. And finally, under input, msmpi.lib. And that's it. And if I restore the zoom on this thing, because I zoomed in on it, we should have the whole program ready to run. So, if you want to find out where this folder is, what we can do is, say, open up, say, File Explorer, and then type in the C folder. Go to Program Files x86. Look for Microsoft SDKs. And then we have our MPI folder here that includes the include folder and the library folder. We need those two paths. And more specifically, we need one of these to be included as part of our Visual Studio project. But once we have that completed, we can proceed with running the program and seeing how it works. So I'm going to move my face cam a little bit. If I build this program now, I press Ctrl-Shift-B, it's going to build, and it's going to succeed. Then I click on the solution here in Solution Explorer, open folder in File Explorer. I go to the debug folder here, and I get CSE-5250 MPI file 2023.exe. If this is a 64-bit build, you'll find an x64 folder here, and then that's where your debug folder is. That's how you get to your executable file. Then we type in PowerShell into the console. Not into console, the address bar of File Explorer. We type in ls to make sure that we have our executable there. It is. Let me zoom in a little bit. And then I can simply type in, well, I've done this a few times already, so I can just press the up key. But you type in npi exec -n, we can type in the number 4 for the number of processes, and then / the name of the executable. And just like that, it works. And if it works for 4 processes, certainly it can work for, say, 40 processes. 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20, 30, 40. That's all 40 processes. So it works. Now, one other thing I said is that we can use a wildcard for our receive function, and it will simply tell rank 0 here. I don't care who's sending me the message. I just want whichever message was sent to me first. So instead of typing in I in there, I can type in MPI any source in all caps. Save. Build. If I have PowerShell still open, I can just clear that and type in the command again with 40 processes. Now I'm getting all 39 messages from all the other processes in whatever order they were sent first. So greetings from process 37, 39, 32, 29, 33, 14, 15, and so on. If I ran it again, it's going to give me the messages in a different order. And this is the nature of parallel programming. We can have these processes complete in any amount of time. So it might be random every time we run the same program again and again and again. Could we use this as a random number generator? I'm not sure. But all we know is that this is random. So that is the basics of getting that's the basics of MPI. That's the basics of getting the program to work. That's the basics of how to install this thing on your own computer. Again, these instructions are specific to a Windows machine. So, next week it might be a little bit of a shorter week because I have things to do out of town. But I might give you a brief homework assignment on pthreads just to pass the time. It's going to be a single part assignment where you simply type in the code from the pthreads section and then time how long it takes. So this is for both sections. You might see that assignment. It's going to be a short assignment, and then we'll get back to working with MPI. So that's all I have to share for this week. And with that concludes the video. We'll meet again next week, and then we'll look into more about MPI. All right, thank you, class.